Welcome back to Data Object Optimization Part 2. This session is all about providing practical demonstrations on how to create optimal data objects for effective use. In this session, we will demonstrate the difference between creating and utilizing base functionality without optimization, versus adopting a structured approach where optimized design is the key driver for effective reporting. For the demonstrations, the following use case have been used as the backdrop. A client is interested in understanding their supplier landscape, with a specific focus on geospatial distribution, and has requested the following views. 1. Total suppliers, how many suppliers are registered on their system? 2. Local versus international, a count of how many suppliers are based locally versus internationally. 3. Geospatial breakdown, a detailed view of suppliers by province and district for local suppliers, and by country for international suppliers. Access was granted to the supplier database, which contains various tables related to supplier information. A Microsoft SQL data source to the supplier database was created and discovered. Based on the data discovered, one core table was identified, namely the master address table, which contains 2.473 million records. Additionally, 5 supplementary tables were identified containing country, provincial, district, municipality, and city information to enrich the core table. To illustrate the impact of design, we will walk through the following 3 approaches and visualize their results using insights. Approach 1. Creating an insights view utilizing multiple Fraxes data objects. We will use multiple Fraxes data objects to create a view in insights and discuss the implications on performance and usability. Approach 2. Consolidated cache data object in Fraxes. Here we will create a consolidated cache data object that satisfies all possible required viewpoints in Fraxes and highlight the benefits in terms of efficiency and performance. Approach 3. Visualization of viewpoint-specific data object. We will design viewpoint-specific data objects for targeted visualization and emphasize how this approach enhances reporting accuracy and clarity. Lastly, we'll recap the demonstrated approaches and discuss the importance of optimized design in data object creation. Without further ado, let's jump right into it. Approach 1. Creating an insights view utilizing multiple Fraxes data objects. In the first approach, we'll demonstrate how to use Fraxes and insights together to meet reporting requirements. For this example, 6 base data objects were created in Fraxes with push enabled. These objects represent all the data needed to build a federated view to meet the reporting requirements. While these are basic data objects, imagine this setup being very complex with a deep hierarchical data structure. Next, we created a view using these data objects in Insights. This view represents all the required data. Often, data transformation is needed within Insights to produce the desired output. Ideally, data transformation should be managed and controlled on a central platform. While this isn't always possible, it's recommended to use Fraxes for most of your data transformation needs. This approach leverages Fraxes' processing power and helps with version control and data standardization. Once the view was built, 5 Insights reports were created which represent the 6 aggregated views required by the customer. Finally, a dashboard was created incorporating these reports. You'll notice that the dashboard renders in about 22 seconds. This delayed response is due to the amount of data that needs to be streamed from the source over the network, before the aggregated queries can be executed to render the reports. While this approach delivers the required results, it does come with performance and change management costs, and is therefore not recommended. Approach 2. Consolidated cache data object. In this approach, a basic federated data object will be built in Fraxes instead of Insights, which will utilize the caching function in Fraxes to improve performance. For this example, a single federated data object was created in Fraxes that consists of the 6 tables required to satisfy the reporting requirements. This data object represents the same data as in the previous approach built in Insights, but eliminates the need to transform any data in Insights. Once the federated data object was created in Fraxes incorporating the 6 required tables and it was published, it was cached to ensure no network latency would jeopardize data response times. All queries are executed against the Spark cache data instead of fetching data from the source. It's worth noting that caching schedules can be enabled with Delta cache refreshes, updating only records that have changed since the previous cache refresh. Once the data object was cached, a view was created in Insights using only this specific data object. As previously mentioned, no additional transformation was required. Following the same process as in approach 1, 5 reports were created which represented the 6 aggregated views required by the customer. Next, a dashboard was created incorporating these reports. You'll notice that the dashboard rendered in approximately 4 seconds, which is more than 5 times quicker than in approach 1. This improvement is due to the queries being executed against the cached Spark table. While this approach significantly improves the timeline for delivering the required results, it's not always possible to use a single data object to accommodate your reporting requirements. Additionally, even caching data objects containing millions of records can result in slow responses, as data still needs to be streamed from Spark to Insights. Approach 3, Visualization of Viewpoint-Specific Data Object. This final approach will highlight how to apply the recommended guidelines described in the first part of this training tutorial. First, 6 push-enabled base data objects were created in Fraxes. Only the required fields were selected. The number of records per data object were evaluated and it was noted that the master address table had 2.473 million records. When querying this table from the source, the speed at which the data would be returned would be severely impacted. Therefore, the data object was cached after it was published to ensure that anyone directly querying the data object would benefit from improved performance. A new federated data object was built using these base data objects, representing the same view as in the previous approaches. To leverage the improved performance of Spark, the federated data object was cached. At this stage, using this data object in Insights, you would expect the same response time as in approach 2. To ensure that all reports on a dashboard render at optimal speed, especially when querying large cached datasets, our recommendation is to create data objects that represent the exact data response required for each report. To do this, 5 data objects were built that represented the exact aggregated responses required for visualization. Since these objects were built off a cache data object, the push indicator was switched off to ensure queries were executed on Spark and not on the source. Once these objects were published, views were created in Insights for each data object. Following the same process as in approach 1, 5 reports were created representing the 6 aggregated views required by the customer. The only difference here was that each report was built off its own view. Next, a dashboard was created incorporating these reports. You'll notice that the dashboard rendered in approximately 4 seconds, which was expected due to the size of the dataset. If the cached dataset was larger, the response would be better than in approach 2. By creating viewpoint-specific data objects and caching them, this approach ensures optimal performance and efficient reporting, especially when dealing with large datasets. In conclusion, we've explored 3 different approaches to data object optimization in Legos, each addressing the client's requirements for understanding their supplier landscape, focusing on geospatial distribution. First, in approach 1, Insights views were created using multiple Fraxes data objects. While this method met the required results, it came with performance costs due to data streaming from the source. Next, in approach 2, a consolidated cache data object was built in Fraxes. By utilizing the caching function, the dashboard rendering time was significantly reduced by executing queries against cached data. This approach highlighted the limitations of using a single data object for all reporting needs. Finally, in approach 3, the recommended guidelines were applied by creating viewpoint-specific data objects. Caching these objects ensured optimal performance, especially for large datasets, resulting in the best response times of these 3 approaches. Here are some key takeaways. Optimization matters. The structured approach of optimized design drives effective and efficient reporting. Centralizing data transformation and leveraging Fraxes' processing power are crucial for performance and standardization. Caching for performance is essential. Caching data objects can significantly enhance query response times, reducing the impact of network latency and large dataset sizes. Creating targeted data objects is vital. Viewpoint-specific data objects tailored to individual reports ensure that dashboards render quickly and accurately, providing a better user experience. Remember that the right approach depends on your specific use case and requirements. Each method has its advantages and trade-offs. By understanding and applying these principles, you can effectively optimize data objects to meet your reporting needs. Thank you for joining us. Should you have any further questions or require assistance, please don't hesitate to reach out. Happy exploring with Legos!